all scientists are good at observing nature. They take lots of observations and see. And where do those observations lead? Those observations will lead to certain patterns. That one might see, patterns or trends. And then from those patterns and trends come laws. Can you think of some observations that led to laws? Well, one I can remember from physics. The apple, falling on, what is it? The apple falling off the tree or hitting Newton in the head. Led to him observing. How does an apple fall from? I don't know if this is true because I never read back. I just remembered this. Then he started observing how the apple falls. Does it fall at one speed or does it accelerate? How long does it take? What's the distance? Those types of things. And from the pattern of how that apple fell, right? He came up with what laws? Well, if you had physics, Newton's laws of physics. So do Newton's laws of physics, is that where we end? We start thinking about, why is the apple falling and where is it falling to, right? And so do you know where Newton's laws end up? There's some kind of hypothesis. What is pulling that apple and where is it going? So what is pulling the apple and where is it going? Where's the apple going? If it didn't hit the ground, where would it have gone? If there was nothing stopping the apple, would the apple have gone to China on the other side of the globe? Or past and shot out into space? No, the apple would have stopped where? Where would the apple have stopped? The apple would have stopped at the center of the earth because what's pulling it to the center of Earth was hypothesized to be what? Gravity, right? And so this led to the hypothesis of gravity, which gave this theory, the theory of gravitational force that are interacting on all bodies. And so this is typically, how it's not always like this, but this is we see this pattern over and over again in science. Right, and so there are a couple of laws, that are in Chapter 1. One law that's in Chapter 1 is the conservation of mass. Have you heard of that law, or conservation of matter? Matter is neither created nor destroyed. In other words, mass is neither created nor destroyed. Have you heard that law? Where did that law come from? What led somebody to come up with that law? Matter is neither created nor destroyed. Who says so? And how do they know? Yeah, from observations, right? Observations say so. For example, the classic observation is a burning candle. Even though the mass of the candle is going down, the gases that are generated equal the mass that's lost by the candle, so that the total mass before burning the candle and the total mass after burning the candle, including the gases, is the same. They're equal. And they did this over and over, and the patterns that they saw was all chemical reactions that they observed fit this pattern. That mass was never lost. The mass initially and the mass at the end were the same. And so this led to the law of conservation of matter. The law of conservation of matter led to what hypothesis? Do you know? And so a lot of people start wondering, so this law of conservation of matter seems to work, seems to hold. They haven't found any violations of it, although more recently they did. Has there ever been a violation of the law of conservation of matter? Yes? No? Yes, in nuclear reactions. In nuclear reactions, mass is not conserved. Some of the mass is converted into energy, or energy be converted. And so there have been modifications to certain laws with time, but the basic principle of this still holds. In chemical reactions, which we'll talk about the difference between chemical and nuclear reactions later, but in chemical reactions it appears to hold. You'd have to go way down to extremely minute quantities of mass to see any difference. Well, anyway, going back to this, what hypothesis did this lead to? The law of conservation of matter. Does anybody know why matter is conserved? You know, people start wondering, okay, this law seems to work. It's like any other law. You know, the speed limit's 65. And you could either follow it, and you're always right on. Okay, I'm going to go 65 within the law. But you might start wondering, you know, why is the speed limit 65 here? Or you might start thinking about, you know, what. And so scientists start thinking, you know, why is matter conserved? Why don't we lose some or gain some? And so the hypothesis, let me just tell you what the hypothesis is. The hypothesis is that matter consists of atoms. And these atoms are just rearranged in chemical reactions. They aren't created or destroyed. And so this led to atomic theory. And so we'll see more examples of this as we go along, but this is the basic scientific method, a couple of examples there. But what is the difference between a law, a hypothesis, and a theory? What would how would you describe a law? Well, a lot of people, when they think about laws, you know, these are just what we call, you know, empirical equations. These are often just empirical equations. Now, what is an empirical equation? Empirical just means based on observation, based on experiment. Experiments are observations. And so these equations come from our observations. An example of this would be this law, PV equals nRT. Where did PV equals nRT come from? Did that come from observations, or did that come from theory? It came from observations. You know, you just observe how gases behave and you fit it. And then there's this fudge factor, which we call R. R is just some variable they threw in there to make it work. You know, but this seemed to fit how gases behave, and it was a reproducible pattern. And then we get this law. But then you start thinking, you know, you could accept this is like 65 miles an hour. That's the speed limit. But you go, why? Why is it set at 65 here and 25 there? You know, what is the reasoning behind that? Well, those types of laws, like traffic laws, don't follow the same set of restrictions as scientific laws. You know, scientific law is different than a traffic. Some traffic laws are just political. You know, somebody lives nearby there, they want the traffic to slow down. Somebody who has influence. But scientific laws are going to be based on something more, based on these observations. Okay, so what is the theory underlying this? Do you know? Everybody can punch these. This is very simple. If you want to solve for pressure, pressure is equal to nRT over V. You just plug in the numbers, punch it in your calculator, you're done. Right? But what if somebody asks you, where did this come from? You know? Why does it work? Of course, anybody can use this. You know, anybody who's had algebra can use this. But can anybody explain the origin of this, or can anybody tell you what the underlying fundamental description of this? And that's what a theory is, the underlying. Let's try to make this legible. fundamental picture of what's happening. This picture we call a description. You know, what's going on? So if matter consists of atoms, what's happening with the atoms that cause them to behave like this? You know? That's what we're looking at. And so, you know, we might want to start digging deeper. We just don't want, there's, in engineering, I took this engineering course, and in engineering they want to get rid of all the other stuff and just come up with one simple equation. You know, this is a big number. You multiply out all the constants and you just plug in the variable. You take the variable, multiply by that big constant, and you're done. You know, they want speed. They don't want to think about all these little things that are going on. But what we want is, we want to start thinking about, where does R come from? Somebody tell me, where does R come from, and why does it equal 0.08206 liters atmosphere per mole Kelvin? Or whatever it is in bar. We'll talk about what it is in bar. Can somebody tell me that? See, and so you're at this level right now. We just want to use this. You know, we want to use this to get some useful information, like an engineer, right? But when you start progressing in science, then you want to start thinking, you know, a little bit more about, you know, I just don't want to use it. I want to understand it, too. That was my problem in thermodynamics at UCLA. I knew how to punch out the numbers, but I really didn't understand it. You know, doing the calculations was simple, and so we need to. Well, understanding it's going to come from some kind of hypothesis. A hypothesis is what we call a tentative, fundamental description. And so what's the difference between a tentative fundamental description and the fundamental description? I shouldn't call this the underlying fundamental description. I should call this the underlying fundamental description that has wide acceptance, you know, or that is generally accepted. Generally accepted. And so usually when somebody comes out with a theory, they test it. You know, scientists are generally skeptic in nature, and they like to attack things to find any kind of potential weaknesses, because it's a self-regulating, like self-policing organization. And you know, in science, one of the things that you got to get used to is being heavily criticized. You know, as you progress in science, that's all you're going to get: criticism, 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 and you know, it's not because they're trying to attack you or get at you. It's because they're just looking for, you know, potential weaknesses so that they don't pursue something that might be fundamentally wrong. And so this is going to be generally accepted, but, you know, a theory, when it's tested, isn't just repeating things. You know, a theory has to do one more thing. A theory not only has to give you a nice underlying fundamental description, like atoms. Atoms are the reason why we have conservation of matter, right? The atoms don't disappear. They're always there. But we also have to be able to test this by predicting new, unforeseen observations. And so a theory's got to predict something that nobody's ever thought of. Unforeseen observations. So actually, we're going to talk about atomic theory in chapter 2, but I just introduced it now. One of the things that atomic theory predicted was something called the law of multiple proportions. So if matter consists of atoms, then these atoms can only attach to each other or bond to each other in, you know, whole number ratios. And whereas, you know, there were competing theories at this time. Competing theory would be like this vapor, you know, and if you have this vapor, then they can attach or bond each other in any ratio, tenths, thirds, whatever ratio. And so here, this theory, atomic theory, predicted the new unforeseen observation was the law of multiple proportions, which was tested and found to be consistent with the theory. There's still people who don't believe in atoms. You know, I was was approached maybe about 5 years ago, and this guy gave me his book that he'd just written. And the book was just matter doesn't consist of atoms. Matter consists of these other things he came up with. But it's a very thick book. But in general, I don't think, I think that was just one person out of a 4.5 billion that really didn't believe in it. All right, so let's go back to observations here. When you take an observation, we call it a measurement. Because, you know, we have two different kinds of observations. We have qualitative observations and quantitative observations. So what's the difference between qualitative and quantitative observation?
Qualitative is words and quantitative is numbers?
Qualitative is words and quantitative is numbers? Yeah, that works. You could use that. Anybody else? Words, yeah, qualitatives can be numbers too. It's just how precise you are. What's the difference between precision and accuracy in measurement? Have you heard those terms before? Precision and accuracy.
Precision is how many times you hit the same answer. And then accuracy would be actually close to the
Okay, precision with how many times you could hit the same thing, and accuracy would be
how close you are.
how close you are. Yeah, exactly. That's it. And so when we're talking about measurement, qualitative measurements are less precise, you know, just kind of general. They're about, I don't know, 50 people in this room or something, 40 people. Whereas more quantitative would have a more precise number, you know, in other words. And so when we're dealing with measurement, these are some things that we should think of when we take measurement. You know, are we measuring an extrinsic property or an intrinsic property? What was the difference between these two again? What's the difference between extrinsic and intrinsic? Is independent of the amount. That's good. But, you know, in certain ways, certain things do depend on the amount. You know, usually the more you have of the stuff, you know, the better the measurement. And so if you're measuring a mass, you know, if you have very like microgram quantities, you know, we have to worry what is the relative error in that measurement. And so we start to think about errors associated with that measurement. And the errors are going to be in terms of what? Errors. What do you know about errors in measurement? All measurements contain uncertainty. And so when we're thinking about, therefore, we must think about error when working with numbers. All right, so what I'm going to do is I'm just going to go, I'm not going to hit these topics one by one. We're going to hit these topics when we're looking at some problems. One of the things in chapter 1, how late do we go till? 10:35? 10:55, good. Okay, one of these things, actually, the approach I'm going to take for chapter 1 is a little different. The approach I'm going to take for chapter 1 is I go through some of the things here, but we're going to go through most of the things when we're working out the problems, most of these review concepts. And so the exercises here start off with the scientific method. I assigned all these. We usually go through what are the principal reasons that one theory might be adopted over a conflicting one, etc. And then we're going to keep going. And so these are basic review problems here. Significant figures, units of measurement, temperature scales, density. All these are good, and you should go through them, percent composition, but I'm going to start here. I'm going to start with integrated and advanced exercises. We're going to look at these at work, and so if these are hard to follow, make sure you go back and take a look at the other problems. And so let's look at number 67 here. Blow that up. Can you see this okay? According to the rules on significant figures, the product of the measured quantities, 99.9 meters and 1.008 meters. So let's do that now. Number 67. So we're going to take 99.9 meters times 1.008 meters. One of the ways we deal with uncertainty is by looking at significant figures. And so how many significant figures does this have? Here. 3 sig figs. And having 3 sig figs here is significant because when we think about this, the amount of uncertainty in there, and this is typically, what, a measurement? Somebody measured 99.9 meters? What would you think? Yes. I think somebody measured 99.9 meters. And so what level of error or what level of uncertainty do you see in 99.9 meters? When you look at that number, do you get a feeling, oh, there's a little bit of uncertainty in there, and I feel it's this much? How much uncertainty do you feel that's in that number? 0.1 is a little high. I wouldn't say that there's 0.1 uncertainty in there. Yeah, I'd say that this number, the degree of uncertainty there is, this number can range from 99.85 to about 99.94 meters. In other words, if the true, let's say the true length of this was 99.85, then you'd round it to 3 sig figs, it'd be 99.9. Or if the true length of this were 99.94, it would have been rounded to 3 sig figs at 99.9. So do you see the uncertainty in this? And that uncertainty is a measure of accuracy or a measure of precision? Accuracy or precision? You say accuracy. Does anybody say precision? Well, I'll tell you, this is actually a measure of precision. Because let's say somebody had a meter stick, but the meter stick, they didn't notice that the first part of it was cut off, and they're taking all their measurements based on a broken meter stick. And so they might get very precise results, 99.9, let's say, centimeters, but they're way off in terms of accuracy. In fact, they might even get even higher precision than that. They might have gotten 99.8 let's say 88 centimeters, estimating down, because this is marked to the nearest millimeter, estimating down to the 10th of a millimeter. But is that accurate? Or let's say this has been sitting out in the sun and shrunk. If it's shrunk, is it still giving you an accurate reading? And so this is a measure of precision. In order to know the accuracy, we need more information. We need to know, was this meter stick calibrated, to make sure it's reading correctly, which we don't have. And so right now, we can just say that this has this level of precision versus something like this. If I had 99.90 meters, is that the same number? Is 99.90 meters the same as 99.9 meters? No, totally different. To a scientist, I look at these two numbers and I go, yeah, those are completely different. Why are they completely different? They're completely different because of the level of precision. This number is much more precise or much less precise than this number? Much more precise. Much more precise is because they're narrowing it down. They're narrowing down the range so that this is going to range from what? You tell me. This is going to range from 99.895 to 99.904 meters. Does that make sense? And so typically when we look at numbers, we put this kind of range on we put this kind of uncertainty on it. The type of uncertainty is half the last, or half the, okay, so we're at 0.9, so we'll go plus or minus 0.05 meters. That degree, right? And over here, this would be plus or minus what? About. Was that, did I write the number right? 1.008 meters. This would be 0.0005. And so we get that kind of uncertainty in the number. All right, now let's go ahead and multiply this out. So if we take 99.9 meters, let's do 99.9 times 1.008, we got 100. Now, our answer should have how many sig figs? Yeah, the rules for multiplication are 3 sig figs, 4 sig figs. Our answer should be the smaller number of sig figs, 3 sig figs. But this is what I want you to do in this class. I want you to get in the habit of writing extra digits. The reason I want you to write extra digits is because I want to see how you round the number. And so what I do is I wouldn't stop here. I'd go 100 points. And sometimes you can subscript it, 6992. Actually, those are all the digits in my calculator. So I'm just going to go extra here. And the units here would be meters squared. All right, so if I were to round this to 3 sig figs, what would it be? This would be 101 meters squared. Right? We drop the 6, round that up. So this would be 3 sig figs. Here. All right, so we're done with this problem. But, what is the degree of uncertainty in this one now? Well, this is kind of a tricky problem, but it's all right. All right, this was about plus or minus 0.05, plus or minus 0.005. So this was much more precise, right? But this is much less precise. And so since this is screwing up our precision, we can't have our answer with this kind of precision, right? And then we look at this one. What is this one? The precision on this one? Plus or minus 0.5. This is crude error analysis, but we're going to do something more sophisticated later with propagation of errors. But anyway, what does this? Should be expressed in 3 significant figures, yes. 101 meters squared, yes. Yet, in this case, it would be more appropriate to express the result to 4 significant figures, 100.7 meters squared. Explain why. And so they're saying that, we shouldn't go to 3 sig figs. We probably should go to 100.7 meters squared, which is 4 sig figs. And so, in other words, they're telling us to violate the rules. Now, what are these rules? Are the rules of sig figs laws? Theory? No. What is a rule, and how does a rule compare to a law? What's the difference between a rule and a law? Rules have a lot of exceptions in general. Rules are just kind of general, rough, qualitative patterns, whereas laws are much more quantitative patterns. Does that make sense? And with these rough, qualitative patterns, there could be a lot of exceptions. And so, yes, we're violating the rules for sig figs, but the rules for sig figs are just simplifications. A lot of times, things are kind of complicated, and so they try to simplify it. And when they simplify it, sometimes they make things even more complicated because there's lots of violations you have to keep track of. Right? And so, in other words, here they're saying that this is better. Why would this answer be better, do you say? Yeah, because this is a better reflection of the uncertainty in our original data. This is overestimating the uncertainty, the 101. And so this would be and this is a very qualitative answer. We aren't getting into quantitative, because later on you're going to learn quantitative rules for dealing with this, in which you don't have to, deal, because the sig figs do have a lot of exceptions. Do you know all the exceptions of sig fig rules? No, because people figure, well, pretty soon you're going to forget about those and go on to this. I mean, we still use sig figs, when we take observations, but when we multiply out and when we divide, it's how the error propagates in the multiplication. Do we multiply the errors here and the uncertainty? What do we do? And that you'll learn later. And so, is that clear? Because this is a better reflection of the uncertainty in our original observations, in our original measurements. Okay, let's go on. Here. 68. Do next. 68. The reason why I want to do these is, you already know a lot about problem solving in Chem 4 or Intro Chem, but Chem 1A is going to be harder, and you're going to see this right away in Chapter 1. And so let's take a look at some of the more challenging problems. For a solution containing 6.38% paradichlorobenzene by mass in benzene, the density of the solution as a function of temperature T in the temperature range 15 to 65 degrees C is given by the equation. Now, you look at this equation. Where did this equation come from? Where do you think? Okay, the density is a function of temperature. And so what they're saying is, as the temperature changes, so does the density. You've seen that before in water. The density of water depends on the temperature. Usually the higher the temperature, the less dense, because the volume expands, the mass stays the same, so the density goes down. And so here, the higher the temperature, it looks like, the density is going to decrease, it's negative. And so this temperature, they use in lowercase t here. But where did this equation come from? This equation came from somebody was there measuring the density of benzene at different temperatures. And so they take their observations. So this is number 68. And so this is what scientists do. They take observations. So the observation would be the density of benzene at different temperatures. Actually, it would be the other way. They set the temperature, measure the density, right? And so they do. They take a whole bunch of numbers down. And so you have all these observations. What do you do next with the observation? You try to find some kind of pattern. Now, how do you find a pattern if you got columns of temperatures? Starting, maybe we'll go from 0 degrees C, etc. How can you usually find a pattern from this? You graph it. And so typically what we'll do is we'll just graph it like this. And so we'll see, the density is decreasing with temperature. And so from this pattern, we see how the density decreases. This looks like what we call a linear function. Linear means what? Straight line. So this looks pretty much a straight line function. So we got some data there, and we'd say, well, the general trend is like this. It's decreasing like this. And then what do we do? Well, what we try to do is, rather than having all this data table and the graph, we try to define how the density changes with temperature in the most concise way possible. And the most concise definition of this change is a mathematical equation. You know, if you can define it using a mathematical equation, that's the best. And so we can get the equation of this line like this: y equals mx plus b. And then if we have y, you know, we just put the density versus the temperature. Y is the density, T is x. And so we can figure out the density at any temperature if we know the slope and the intercept, mx plus b. And so y is the density, m is the slope, x is the temperature, plus the intercept. The intercept we get here. That's much better than having a data table like this, and it's much better than having a graph, because if we have a simple equation like this, we'll just plug in the temperature. But how well does this fit? You know, does this come from theory? Theory is the fundamental. No, this is what we call what do we call this equation? A empirical equation. What is an empirical equation again? What's an empirical equation? An empirical equation later on is a law. A law is a little bit more than... laws are based on empirical equations. So the first step is to get the empirical equation. And then usually what people do with laws is they test them. They look for violations of the laws. Have you heard of the laws of thermodynamics? You know, people have been trying to find violations of the law of thermodynamics for hundreds of years and haven't been able to yet. And so usually they get a law like this and they say, well, I don't really, you know, because does that really fit, you know, the data? We don't know how good the data is. You know, just because somebody came up with an empirical equation, we don't know. Does it really fit the data? What happens over here? You know, the equation goes down here, but the data points are out here. Is that a good fit? Is this empirical? No, because there's something kinking here, and that should be incorporated into the equation, but it may not be. Just because you have an equation that seems to fit the data, we don't know what the data looks like, and we don't know how reliable it is. And so usually when you have a law, people have been testing it. Lots of different people have been testing it and making sure it fits consistently. And just because somebody throws out an empirical equation doesn't mean anything just yet. You know, to be a law, it has to be subject to more rigorous evaluation than that. But anyway, some of these fits are good. Some of the fits aren't so great. Usually, you know, when we come up with our empirical equations, we're going to come up with some kind of fit. You know, if we come up with some empirical equation fitting the data, we want to come up with some way of expressing the uncertainty. Let's say this were based on 2 data points. Someone, you know, they're lazy. You know, I don't want to collect so much data. I just want to, I'm going to just collect 2 temperatures and 2 densities. That's enough. 2 temperatures and 2 densities, and I'm going to come up with this empirical equation, which is here, and give it to everybody. This is the law, you know, my law. How confident would you be in that? You know, if there were only 2 data points here versus somebody else who goes crazy and gets thousands of data points, and they get thousands of data points and it's all lined up like that, you know, which one are you going to have more confidence in? The person who took thousands of data points or the person who only took 2 data points? Thousands. But the person who took 2 data points, they give you this equation, and the person who took thousands of data points gives you an equation. How do you know which equation is more reliable? You just have the equation. Is there any other thing that tells you the uncertainty in that equation versus this equation? You see, in science, we just don't give equations out like this. You have to also tell about the degree of Yeah, not accuracy, because accuracy, the way we explain accuracy is this. You tell the person how you took the measurements. And based on how you took the measurements, then you can go, well, it's most likely fairly accurate. We do something called calibration. And so when we're given an equation like this, okay, somebody shoots out this equation. I don't know how good this equation is. If they took two data points always define a straight line, but the third data point might be out here. If the third data point's out here, was that a very accurate description of density? No, not at all. And so, so those are the things we think about, and those are the things you're going to have to think about, because we're going to start taking measurements soon, and you're going to have to come up with some interpretation of the error associated with the measurements. Okay, we'll stop here since we're out of time.